Welcome to Cosmic Monologue. I'm your host, and we're diving into one of the most fascinating and extreme topics in astrophysics: black holes. This episode is all about what really happens if you fall into one. Not myths, not science fiction, but what physics tells us so far. We will cover how black holes form, the structure around them, the strange effects of relativity, the process known as spaghettification, and what modern physics still doesn't know about the singularity at their core. So let's get started. Now, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The idea dates back over 200 years. In the late 1700s. Jean Mitchell and Pierre-Simon Laplace speculated about dark stars with gravity so strong that light couldn't leave their surfaces. But the modern concept of black holes comes from Einstein's theory of general relativity, published in 1915. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. In 1916, I'm going to mess his name up, Karl Schwarzschild found the first exact solution to Einstein's equation. It described a point mass with an event horizon, what we now call a black hole. So in simple terms, a black hole isn't an object in the usual sense. It's a region of space where space-time itself curves inward so steeply that nothing inside can get out. Most black holes we know about are formed from the deaths of massive stars. When a star several times larger than our Sun runs out of nuclear fuel, it can no longer support itself against gravity, so its core collapses. If the remaining mass is more than about 2 to 3 times the mass of the Sun, even neutron degenerate press, or the force that holds up neutron stars, isn't enough to stop collapse. Gravity wins completely, and a black hole forms. There are three main categories of black holes we know about: stellar mass black holes, typically 5 to 20 times the mass of the Sun; intermediate mass black holes in the hundreds to thousands of solar masses; and supermassive black holes, millions or even billions of solar masses, found in the centres of galaxies, including our own Milky Way. Our galaxy's central black hole, Sagittarius A star, is about 4 million times the mass of the Sun. To understand what happens if you fall in, let's talk about the structure around a black hole. Now, there's the thing called the event horizon. This is the boundary. Once you cross it, nothing. No signals, no light can get back out. For a non-rotating black hole, it is a perfect sphere. The accretion disk, something around that name. Many black holes are surrounded by hot, glowing disks of gas and dust spiraling inward. This material gets extremely hot and bright, emitting X-rays and sometimes jets. Singularity. At the very centre, general relativity predicts an infinitely dense point where space-time curvature becomes infinite. This is where our known physics break down. If the black hole is rotating, which most likely are, things get even stranger with regions like the ergosphere, where space-time itself is dragged around. Now, imagine you're falling in, strictly as a thought experiment. As you get closer, you would notice some dramatic effects caused by general relativity, like gravitational time dilation. To an outside observer, your clock appears to tick more slowly you get closer to the horizon. To you, time feels normal, but to the outside world, you seem to freeze as you approach the event horizon. Gravitational redshift, light leaving you, would appear more and more redshifted, stretched to longer wavelengths until it completely fades out as you reach the horizon. From the outside perspective, it looks like you never cross the event horizon. But from your perspective, you do, and there's nothing special at that exact crossing point. You don't feel a wall, you just pass through. Now, to summarize spaghettification, which is what we're going to go next, the best way that I can summarize it is inside the horizon, things change dramatically. So, one of the most famous predictions is spaghettification. This comes from tidal forces, the same kind of forces that cause ocean tides on Earth. Imagine your feet are closer to the black hole than your head. Gravity is stronger on your feet, weaker on your head. The difference creates a stretching force. For small stellar mass black hole, the tidal forces become fatal well before you reach the event horizon. You'll be torn apart long before you cross. For a supermassive black hole like the one at the center of our galaxy, the event horizon is so far from the singularity that tidal forces at the horizon are actually weak. In that case, you could cross the horizon without being spaghettified right away. Only as you fall further inside would those tidal forces eventually become strong enough to rip you apart. Once you cross the event horizon, escape is impossible. Every possible path forward leads deeper in. According to general relativity, the singularity lies in your future, just like tomorrow lies in your future now. That means once inside, you can't avoid it, just as you can't avoid time passing. What happens at the singularity itself, you may be asking? Well, that's where our knowledge ends. General relativity predicts infinite density, but infinities usually mean that the theory has hit its limits. Most physicists believe that a complete theory of quantum gravity, something that unites general relativity with quantum mechanics, will change this picture, but we don't have that theory yet. Black holes are not just theoretical, we have strong observational evidence. In 2019, the Event Horizon Telescope released its first image of a black hole shadow in the galaxy M87. In 2022, the EHT released an image of Sagittarius A star, our own galaxy central black hole. We've also detected black holes colliding through gravitational waves using LIGO and Virgo observatories. These ripples in space-time confirm Einstein's predictions with incredible accuracy. But mysteries remain. What happens to the information that falls into a black hole? This is the information paradox. Quantum mechanics says information can't be destroyed, but general relativity seems to suggest it is. Resolving that conflict is the deepest problem in modern physics. So, to sum up, if you fall into a black hole, here's what physics says. From the outside, you appear to freeze at the event horizon. From your own perspective, you cross it normally. If the black hole is small, tidal forces kill you before you reach it. If it's supermassive, you cross unharmed at first, but eventually tidal forces stretch and tear you apart as you approach the singularity. And beyond that singularity, we simply don't know. Our current physics can't describe it. Black holes are not just destructive monsters, they are extreme laboratories for testing the laws of physics. They stretch our understanding of space, time, matter, and information to their very limits. That's all for today's episode of the Cosmic Monologue. Thanks for joining me in exploring the facts about what really happens if you fall into a black hole. If you have any theories, please, you can leave them in the comments and I will read your theories, because this whole astronomy really has started to interest me now. And I want to share that knowledge with you guys, which is why I'm now doing these videos. So if you have any of your own theories, please leave them in the comments. Until next time, keep looking up and keep questioning.